Good evening. In the next 15 minutes, I'm going to try and convince you that HBase is the right choice when it comes to real-time column-oriented databases. And I should insist on the real-time part of the sentence. Let me give you the big picture of what you are about to see. This presentation will be divided into two major parts. First, a description of HBase, and second, the demonstration of its use in the context of a project that involved mobile applications, geolocation information, and a potentially huge amount of real-time data. Hopefully, I will provide enough insights to be able to answer the ultimate question: is HBase the right solution for real-time big data storage? First, HBase. So what is HBase? Well, HBase is defined as a distributed column-oriented database that is built on top of HDFS. On HBase website, it's even stated that it's the Hadoop database. It's a NoSQL open-source project modeled after Google's Big Table. It's built for billions of rows and millions of columns with thousands of versions. You will see that it's an easily scalable, strictly consistent, multidimensional system. In the CAP theorem, HBase is a CP-type system, consistency, partition, tolerance over availability, yet it's still highly available. For the record, it's been hosted as a top-level project by the Apache Software Foundation for 5 years this month, so happy birthday! How does it work? Well, I'm not going to give you the full details, but you should know that the data is first written in WAL, write-ahead logs, and from there the key values are saved in memory stores. Then when it reaches a certain size, it's flushed to disk as H-files. Those H-files are stored in region servers, which are the unit scalability in HBase, and these region servers are monitored by a master node with the help of Zookeeper. So whenever you want to write data to HBase, you will use any of its APIs and let the system walk its way through WALs, memstores, then H-files on region servers. In the end, a region consists in a sorted contiguous range of rows. Region, rows, let me confuse you a bit more by adding tables, columns, and cells. As you remember, we defined HBase as a column-oriented database. This columnar nature found its meaning in the fact that the column is the basic unit in HBase. No matter what, columns will be stored in the same region servers. A column may have multiple versions, distinguished by a timestamp representing the time it was written in HBase. Each of these versions are contained in what is called a cell. Columns are grouped in column families. One or more columns form a row that is uniquely addressed by a row key. Finally, all these rows form the table. You could see on the graph how it would look like. When scanning this table A, for instance, if you don't specify the number of versions you wish, you would get the latest versions of cells, the ones in bold. But it's up to you to specify what you need. Let me conclude on the mechanics behind HBase by precising a few key features. Each cell consists in a key value pair, the key being the concatenation of the row key, the column family name, the column name, called column qualifier or the quali if you want to get fancy, and the timestamp. This timestamp allows for versioning and the time to leave feature we already saw in Cassandra. Row keys are sorted in lexicographical order for each table, and columns within a family are sorted and stored together in the same region server. Two less good news. Unlike relational databases, table design is almost schemaless. You need only predefine your column families, as columns are defined only when written. And this last feature implies the less good news: if not defined, a column doesn't take place. In other words, nulls are free. Okay, that's enough with the technical details. Now, what do you want and when do you want to use HBase? If your project mixes a very large amount of data with a need for fast random access, that's what it was designed for. For smaller systems, RDBMS would be much more convenient. But once you really need to scale, and scale big, HBase will definitely relieve you from the burden of scaling RDBMS. Follow my gaze. There are other cases which imply the use of NoSQL database. For example, you may choose Cassandra over HBase if consistency isn't your main concern. But to build upon the shared use of HDFS, you should favor HBase when combined with batch MapReduce jobs. As you can see, large companies already use HBase. Facebook, Twitter, Even in my home country, people are using HBase. Wow! Just let me wrap it up for you before we move on to the project. The pros: fast real-time random read-writes, scalability, consistency, remember that replication comes from free in HBase, and the Hadoop ecosystem integration and community. The cons: well, don't imagine you are going to use it as a replacement for your relational database system. There's no joins, no query engine, no types, no SQL. Even though you can add Hive on top of it to build your queries, it's not native. Transactions and secondary indexes only exist as add-ons for now and are still quite immature as I understood. Also, configuration could be touchy, and it's CPU and memory intensive, so it might have quite an impact on your budget. And I'm not sure whether it's really a drawback, but you do have to unlearn what you've learned when it comes to designing your tables. DDI, denormalization, duplication, and intelligent keys, is the new paradigm. One last thing before diving into the project: the installation process is quite straightforward. All the details are in my report, but if you follow the simple instructions on this slide, you should be able to run HBase quite easily and rapidly. At last, the project. Well, as I quickly mentioned it in my introduction, I studied HBase in a particular situation where we would need to store huge amounts of information from a carpooling mobile application and be able at the same time to serve the queries of its users to locate the nearest other users, depending on their status, their position, etc. Our focus was on HBase real-time capacities, but incidentally, it helped us demonstrate the ease of use of its Java API. But the point was really to assess HBase as a real-time solution for our problem. How did we do that? Well, first of all, this comes from a real situation, and as it happens often in real situations, you don't get to have data before you start collecting it. And that's where you could say you're stuck. Well, hopefully, we knew how the data to ingest would look like. It's a JSON object with the geolocation coordinates of a mobile phone and details on its user and the device. So I created a dataset, and then I created a simulator in my Java program that would act as a data producer to feed HBase at a regular pace, as if we were in a real situation with a continuous stream of data. We didn't have time, nor was it the focus of this presentation, but this whole feeding process should be implemented using solutions like Kafka or Flume. So I left it to my other colleagues to introduce these technologies for us. The second part, our simulation, was to emulate the random access queries. I skipped the details for now, but you will find them in the report file attached to this presentation. To keep our focus on HBase, I copied in this slide the main lines of code we use to query HBase using its Java API. And as you can see, not only is it very straightforward, but it's also very easy to manipulate. Each time, you would connect to a table using the first 3 lines of code with a try-catch block. Then you would use methods of different objects, such as the HBase put object to insert data, the HBase get object to retrieve individual records, or the HBase scan object to get a list of rows according to some filters that would mostly work on the row key to determine which rows to return to you. Once again, all the details are in my report. Feel free to use it. Now, what clearly appears to be the hardest part was the table design, and most of all, the design of the row key. There are many advices you could find on books or on the web, but in the end they all seem to converge to one sentence I found in different slide shares. Design for the questions, not for the answers. In our case, the main question was going to be, what are the nearest drivers for a passenger located at a particular position? That's why I finally decided to use the GeoHash algorithm as the first part of the row key. Combining the features of this algorithm with the sorting of row keys in HBase, I knew that a range of contiguous rows would very likely be close to one another geographically. Once again, the details are in my report, and the book HBase in Action actually makes use of the GeoHash algorithm in another way I encourage you to study if you need this kind of feature for your applications. At this point, the JSON object cannot dictate the column family structure. I just shortened them to as little character as possible to lighten the storage, because it's information that would be repeated in each cell. So we have a table design. Our table was called geo-hashed, by the way, and all I needed to do was to create it. And as it's a one-time operation, I did it using the shell. And it's as simple as the one line you see. Remember, the table only defines its column families, and there's no types. Of course, there are options like TTL or number of versions to keep, but all it takes is one line of code. So let's do it, and let's test our program all together. So as you can see, I'm using a VM already installed with a yarn, and once in my directory, I can start the HBase master and the HBase region server at first. So let's do this. It's not going to take long. That's it for the master. We're on the local VM for this exercise. Okay, so let's go now to create the table. We go to the shell. As I recorded in my bash profile the path to HBase, I only have to type HBase shell. We're in the shell, and now let's create the table. So the first part is the table name, then the column family names. And that's it. It's created. I could use the describe command to see how it's been created. Okay, I got my 3 column families, D, L, and U, which are sorted. And the TTL is forever, for instance. The minimum versions are 0, the total versions are 1, and that's it. Let's exit, and let's try our test dataset, as it's the fastest one. So this is my jar file, hbase.jar. This is the name of the test, and of course it's not working because I'm not in the right directory. It's in the bin directory. Okay, real time. Well, there you go. Up. So it's starting, and there's going to be a lot of information from Zookeeper, which I wasn't able to stop, even tweaking the configuration files. And there it is. The last query took 226 milliseconds, and as we can see, we had results somewhere, I hope. Not sure on the test result, maybe not. But trust me on this, we had results on this one. So let's go back to our... So we tested. So what result did it give? Well, it actually kind of blew up our VM, because whereas the average response time to the simulated queries was around 200 milliseconds, when the dataset was small, it went over 4 seconds per query with a true large dataset. And it wouldn't be acceptable, you know. So just to demonstrate that the queries were actually returning the right answers, I used one response and placed the return points on a map centered on the geolocation of the requester, and that's the Google map in the bottom right of this slide. So, to figure out how and if it would scale appropriately, we decided to create a cluster in Amazon. Once again, I passed the details, but all you have to know for now is that I set up 4 EC2 instances, and I used the Cloudera manager to build the Hadoop cluster. Finally, I ran the program. The average response time corresponded to what we saw for small datasets in our local VM, around 200 milliseconds, and for the largest one, it only grew up to 500 milliseconds in average. Therefore, we knew that it was only a matter of tuning the size of the cluster depending on the actual size of the incoming feed. and to get responses faster than 200 milliseconds, we would probably have to attack the feeding process using Kafka or any other solution. In conclusion, I'm personally convinced that HBase is the right choice for this kind of real-time project. I know it shines with huge datasets spread over large clusters. I would only draw your attention on two things. First, the key point in HBase design is the row key. And remember, in the DDI paradigm, use duplication of contents to create as many tables as you see fit to answer all your questions. And the second thing is that HBase couldn't really work all by itself. It needs to be served by scalable data producers and data consumers. That's why in a production environment I would probably couple it with a messaging platform such as Kafka. Thanks for listening. I hope you'd like using HBase as much as I did.